right. Welcome to the 8th episode of Neural Information Retrieval Talks. My name is Sergi Castella, as usual.
I'm Andrew Yates, University of Amsterdam, as usual.
Yeah, and today we're here to talk about ColBERT, which is a method that, method, model, algorithm, approach, I don't know.
Several methods at this point, but I guess we'll get into that.
Which is something that we have referenced quite often in the past. It's kind of a pretty popular approach in information retrieval right in the last couple of years. So can you just give a few, tell us a few words about why we chose ColBERT and what kind of is?
Yeah, so we've talked, I think, a good amount about dense retrieval methods in general, but ColBERT is a little bit different than the others, and we haven't talked about it specifically. So the way it's different is that most dense retrieval methods, or at least the ones we've talked about, have a single vector. So you have a document. This is a single vector representation. This is great as long as your document is small enough to fit inside a single vector. And ColBERT takes a different approach where it saves the term embeddings or the vectors for each term. Contextualized term embeddings is a normal term for each document. So you can imagine that this increases the size of a document, but it's also increasing the expressive capacity a lot because your representation size grows with the document, and this seems to have nice properties. So ColBERT methods have different points on like the efficiency effectiveness trade-off than dense retrieval methods or than rerankers that we've looked at.
Mm-hmm. No, I think that's a very interesting point because I have made also this mistake in the past in the previous episodes. So kind of like to make the simplification that in neural retrieval you basically found dense retrieval methods or cross-encoder, some form of cross-encoder methods, and ColBERT is pretty much some sort of in between that try to maximize some trade-off between the efficiency and performance that you find often in these methods.
Yeah, it makes the classification a bit difficult. So cross-encoders are always re-ranking because you get query and document at once. Bi-encoder means you're taking the query and document separately, but then it becomes complicated because if you do this, if you process a document separately, you can go the ColBERT way and save individual terms, or you can go the other more common and other model way, dense retrieval, of just one vector for the document. But they're both dense, but one is like at the document level storing vectors and one is at the term level. So it's a bit confusing.
Do you know, by the way, what ColBERT stands for?
No, I'm not totally sure, but according to their website, it's supposed to be pronounced ColBERT, which is the name of some comedian on TV in the US. So I'm not sure if they have an acronym for it or if they're just trying to get ColBERT from BERT, or I'm not sure. It looks a little bit like ColumBERT to me, which has some relationship to things we'll say in a minute, I think.
Yeah. But wait, I kind of didn't mention this before, but ColBERT has two main papers right now, one from April 2020 and the other one from December 2021, which was actually published in NACL 2022, which was just...
Yeah, I was just there a week or two
ago. Summer 2022. So we're gonna just go through these two papers a little bit kind of from a high level perspective and going into some of the details. So I think it's interesting to focus first on the original ColBERT paper. On the figure 2, they have some kind of nice representation of sort of like the at the time family of methods for neural retrieval. So maybe you can kind of walk us through that.
Yeah, so to put this in context, this is one of the first dense retrieval methods. So dense retrieval wasn't an established thing at the time of this paper, really. So in the figure, they show two paradigms from pre-BERT methods, which they call representation-based similarity and query-document interaction. So representation-based is what you think of with a bi-encoder. You create some query representation, create some document representation, and they interact in some lightweight way. Like you take the dot product.
Yeah, and normally this normally is performed with dense embeddings, right? Although you once mentioned that there's some approaches that try to do some representation learning with sparse embeddings. Would that kind of fit this category of methods? Or is this only for this kind of dense representation cosine similarity?
I would think of dense representations. It might fit the other category. I'm not totally sure without looking back at the paper a bit. But yeah, so this was common before BERT, and with BERT we still have this. This is just the bi-encoder paradigm. It's fairly standard. The next one that they call query document interaction was essentially like the cross-encoder, you could think of it, variant of these methods, but there was no cross-encoder because there was no BERT. So if you represent query and document as static embeddings, then this is essentially creating a similarity matrix. So for every query term, you have the similarity to each document term. So this is a row or a column in the matrix. We'll say column. And then another column is another query term similarity to every document term. And so this was really common pre-BERT. You construct a similarity matrix like that, and then you have some machinery to consume it. So maybe you use a CNN to try to find like n-gram patterns. Maybe you build some sort of histogram to try to characterize the similarity levels of the document against each query term. It's a lot of high matches, some medium matches, some low matches, this sort of thing. But however you do it, you take that similarity matrix and you come up with a score for that query document pair. That's a product of that similarity matrix. And as I said, this was pre-BERT. With BERT-based models, so actually there's a paper, I was one of the authors, Cedar, where they essentially take these similarity matrices and they just, rather than building them with static embeddings, they build them with BERT contextualized embeddings, and then they score as normal. And this is very similar to just scoring with mono-BERT. So you can predict a score directly from the CLS token, or you can use the contextualized embeddings, plug it into something earlier, and the effectiveness is quite similar in both ways.
Okay.
So the next is all-to-all interaction. This is essentially cross-encoder. Just feed query and document as input. They can interact in the transformer in some way. We don't specify. The transformer handles this. And then you get out either a score or maybe contextualized embeddings that you can create a similarity matrix with. The score is a more common approach.
And this is a clear example of some very intense computation you have to perform during the inference time for each query.
Right, because you're inputting this into the transformer inference time. You can't pre-compute it. And if you're using something like BERT-base, around 110 million weights, around 12 transformer layers, something like that. And then, of course, it gets larger, right? So it's a significant amount of computation. You could only re-rank like 100 or 1,000 with a reasonable speed at inference time. And then finally, they have late interaction, which I would personally call a special case of this similarity matrix. So in late interaction, they're creating these query and document embeddings separately. So passing the query in, creating embeddings, passing the document in, creating embeddings. So this is BEIR. And then with those embeddings, they're basically max pooling over the query terms in the similarity matrix. So for each query term, they're finding the maximum document similarity, where similarity is cosine or dot product, saving that value. They then sum these maximum values. So you can think of it as pooling over the query columns in the similarity matrix followed by a summation would be equivalent.
Okay.
But this is basically what they introduce. So the idea is you can create these contextualized embeddings offline and then at runtime do this comparison of the embeddings rather than having to process them as you would with the reranker.
And then I'm guessing that you need to do, you're summing over all the query terms. So I'm guessing you have to do some normalization of the query length or terms, or?
Surprisingly not. So the query is constant, which is maybe what saves you here, right? Because you're always ranking against a query. So the query length is fixed. But they literally just take the dot product or the cosine similarity. They look at both between them and sum them together.
Okay. All right. That said, I think we can describe the architecture of ColBERT a bit more in detail.
Right. So I guess the query is always 32 terms, and it's either truncated or padded. So they padded it with mask tokens, I believe, as a kind of a query expansion idea.
Yeah, it's interesting. Like they consider that to be a query expansion, right? It's not like you zero out the mask. You just kind of learn some interesting representations from that are probably going to be helpful for the retrieval?
Yeah, so I guess exactly. They learn some representation for these mask tokens, and then they include them in that maxim similarity computation. And I think really that's the rest of the architecture. So that's the query encoder, the doc encoder, same thing. It's just a transformer, converts the doc into contextualized embeddings, and then they perform maxim on those embeddings. So it's fairly straightforward. Their insight here is probably to keep the actual embeddings rather than trying to have a single vector. Which improves effectiveness, but you also have to store them.
Indeed. So I think that the method is pretty straightforward to understand, like you've already explained. So the next interesting thing to look at is that you can use this method as both a reranker and as a full end-to-end retriever system, right?
So with a single vector, you would just use approximate nearest neighbor search, find the approximate nearest neighbors of your query. Here are your documents. Maybe you find the exact distance to re-rank them. I don't know, but it's simple. Here you have a lot of vectors you need to find the nearest neighbor of because you have a vector for every query term. And of course, there's no guarantee that the nearest neighbor of query term 1 will appear in query term 2's top 100 or whatever, right? So what they do is they have a retrieval and a re-ranking step. In the retrieval step, they basically find candidates for every query term. So they find K prime candidates for query term 1, K prime for query term 2, and so on. And so this gives them a set of document candidates. And then in the re-ranking, they just compute exact scores using maxim for each of these candidates. So if it wasn't clear, in retrieval, they're just maximizing similarity to a single query term in order to make the document a candidate to retrieve. And then in re-ranking, they're doing the actual computation to get the full score and then ordering them based on that full score.
And the sizes that they are working with at the second stage, where they compute the full maxim score?
K equals 1,000. So both K prime and K are 1,000. So they take the top 1,000 candidates for every query term, and then they return the top 1,000 after re-ranking these.
So 1,000 per query term, that would be like up to 32,000?
Right, so up to 32,000 if they're all distinct.
Ooh,
and then they re-rank these 32,000 and return the top 1,000.
With the full maximum, which is still like a very big set of documents to re-rank if you were talking about some cross-encoder or something.
Yeah,
like that,
for a cross-encoder, it's a lot. But here they've already loaded these documents into memory, right? So there's very little to do. They just need to do the full computation.
Yeah.
So here, it's not so much the computation that's not necessarily a bottleneck, but it's not the computation that's a problem so much as the storage. Problem's not the right word, but storage space is what this approach requires, not extra computational power.
Right.
I think they consider both quantization and a dimensionality reduction. I'm not sure offhand what combination is shown in the main results table, but there's like a space footprint table where they look at different combinations.
I see.
So for example, if you use 128 dimensions, so BERT is 768 by default, so this is reducing it to 128, and 4 bytes per dimension. I believe this is standard. Float 32, that would be that's standard.
16, so that's half precision, right? I know 4 times 8. Sorry,
4 times 8. Yeah. So this would be float 32.
Sorry.
Yeah. So this is 286 gigabytes.
Okay.
So I don't know what that data file is on disk, but it's under 10 gigabytes.
Okay.
It's a huge amount of space.
Yeah.
And they get this down all the way, for example, going from 128 to 24 dimensions, going from 4 to 2 bytes per dimension. So float 16, they get it down to 27 gigabytes. So it's still more space than the raw text, but becoming reasonable.
Yeah. By the way, Andrew was referencing table 4 in section 4.5. All right, so the methodology they describe how they use MS Marco and TreKar for their training and evaluation. We were discussing before recording this. It's a little bit unclear how they what triples they use of of positive and negative document pairs they use. Right?
Right. So they say they use triples, which I interpret as using the MS Marco triples file. I didn't go look at the code. It wasn't totally clear from the paper only. But I think this is the case. This predates like the hard negative mining and so on.
Yeah. Actually, you were making some very interesting comments on what is considered hard negative mining in information retrieval, and it's kind of a bit unclear because. So I asked you, are they using hard negative mining here? Because I know that hard negative mining is a very popular term used right now, and for dense retrieval, we've talked also about this. It seems to be very important to mine quote unquote hard negatives for a model to learn a very good dense representation for retrieval. So I asked you whether here they were using hard negatives or not. And you said that they were using the MS Marco and...
I said they were using the MS Marco triples. We discussed a bit if they were using BM25, but what I said is I think has been a change in whether BM25 counts as hard negatives. So to me, very technically, a hard negative is from the perspective of a model. This is something that might be confused, right? So think about something like ants where it's finding nearest neighbors of documents. This is from the model's perspective. Like with the model's representations, these documents are close to one another, but one is negative, one is not. So it's a hard negative. It looks like a positive, but it's not.
Yeah.
This also comes up with like topic-aware sampling where you cluster by query. So because the query is similar, this seems to also make it hard for the model. BM25, I don't personally view as hard negative mining, but people are starting to call it that, I think. Maybe because they want to use the phrase hard negative mining so that, this isn't left out. I'm not sure. But like BM25, is clearly hard from the perspective of BM25, which is very different than a dense retrieval model. Like, very, very different. But
no, that's very interesting. All right, another kind of a bit of topic that I don't quite understand is it seems to me like the terminology for cross-encoders and all-to-all interaction, and it doesn't seem very much converged into like people call the same thing different names type of scenario.
Part of this goes back to like the pre-BERT nomenclature. So like DRMM, one of the earliest papers, deep relevance matching model, introduced this terminology of interaction based and representation based.
Okay.
Interaction is something like comparing individual terms, something like that. Representation is something like creating representation from individual terms and then comparing these representations that represent a lot of the document, if not the whole document. So this is kind of analogous to BIencoder or cross-encoder, but it's pre-BERT, and BIencoder, cross-encoder, it's a terminology that works for a transformer, but it's not so clear exactly what you would say for another model, I guess.
Yeah.
So there's kind of a switch in terminologies. People also say, rather than BIencoder, things like dual encoder also, or two towers model or something like that. The point just being the two inputs are processed separately, I think is what's key there.
No, that makes sense that it would relate to the transformers or like this method. Okay, so I think that we can jump into we've covered the methodology. We should I think jump to the most interesting or most relevant results. So which table would you want to focus on? Maybe you can
let's look at table 2 maybe.
Yeah.
So here we have re-ranking results and end-to-end retrieval results with ColBERT. This is compared to the reasonable baselines at the time, which are not dense retrieval methods because this was, among the first essentially. So baselines are things like a BERT-based cross-encoder, doc to query. I believe we've talked about this. This is doing document expansion with a T5 or a generative model. So taking the document, adding some terms to it, and then retrieving it with something like BM25 is normal.
Yeah.
The T5 variation of doc to query, BM25, and then deep CT is a learned sparse representation. So we've hinted at this briefly before. This is one of the very early learned sparse approaches. It's basically learning term weights that can be used with an inverted index. So compared to all of these, we see ColBERT is competitive with BERT-base, maybe slightly worse depending on which row you look at. These authors train it seems a little bit better than another row they cite. It's also a little bit lower than BERT large, so we're talking like 36.5 for the cross-encoder versus 35 for ColBERT. So not quite as good re-ranking, but already quite close and much more efficient. So if you look at latency, this is 61 milliseconds versus like 10 seconds. Right, so that's
from a usability perspective, it's night and day.
Yeah, it's a huge difference.
So I guess the gist of it is like it's much faster and it's comparably performant, not quite, but comparably. Right, comparably. And you can see also in Figure 4, there's also a nice kind of visualization of the flops required, right? For is it inference or?
To re-rank at depth K.
Exactly. And the difference in orders of magnitude is around 2 to 4 orders of magnitude, right?
It's so much faster.
Exactly. I don't think we need to get a lot more in the details of the results. Something that I would like to comment on though is in the ablation studies that they do in section 4.4. The kind of contribution to performance that each of the techniques that they introduce kind of introduces. And I guess to me the most interesting one is this max sim operation. So if you look at the Figure 5, their model B, say ColBERT via average similarity instead of, so basically computing one score per query document representation, right? How much the performance degrades versus model D, which is the comparable full ColBERT model, right?
Right.
Which clearly degrades from 0.32 to 0.26 or something like that.
Yeah, it's a very large difference.
And I think that's very interesting because when you think about it, like the maxim score is not, it doesn't have any learned parameters, right? So it's kind of like not, I don't know how to describe it, but it's kind of
Yeah, I mean, the similarity operation itself doesn't have any learned parameters, but the embeddings going into it are affected by learned parameters, right? So the transformer is producing some embeddings or contextualized embeddings vectors that will eventually be used in maxsim.
Yeah.
There's room to tweak these, but not the actual similarity.
But I mean, my understanding though is that in this experiment they retrained the. Or maybe I'm making too many assumptions
I see what you mean. Yeah, I think they are retraining it.
Right.
I think what's going on here is similar to what we even saw with pre-BERT methods, where average pooling is just not a good way to pool things, it seems. I think what happens is it's just dominated by small, meaningless low values.
Yeah.
Like 0.1 versus 0.4, it's probably totally meaningless.
That's such a good point. I remember, I don't know, actually I'm going to ask you, one paper that made the kind of conclusion that max pooling is often preferred when it comes after a transformation. Or some, maybe I'm not quoting this right, but basically whenever you want to aggregate information from multiple embeddings, you should do a transformation followed up by a max pooling, and that works better. Seems to always work better than something and an average pooling, like you were saying.
Yeah.
And I don't know what's the intuitive kind of like. I mean, you were saying like maybe there's a lot of irrelevant signal kind of being pushed up by the average, right?
Yeah, I mean, think about like confidence. So you might be confident this is a really good match to one query term, and maybe you're wrong about the level, right? Maybe you're wrong that it's a 0.9, it should be a 0.8, right? But you're confident it's a good match versus just something in the middle. So if you give me like Amsterdam and I don't know France, I don't really know what this should be. Like, is that a 0.2 or a 0.4? But this is going to matter when you do the average because this has a big impact. It's probably, I don't know if it's even possible to estimate these well, but even if there is a real similarity that makes sense there.
Yeah, in which you want like kind of just discard that, not have it have any contribution.
Yeah, it's kind of like focusing on the matches where it's clear these are related rather than requiring that you're very right about the relatedness between all pairs. Something like that is my intuition.
Interesting. But I think it's just probably one of the most. I mean, this is the ColBERT is the first paper who introduces this maxim operation.
Yeah, I mean, I think this is just max pooling, and it's been used before BERT. But
absolutely. I mean, when you think about it, this maxim operation is simply like defining kind of like a set to set distance, right?
Yeah. That's a good. Yeah.
That's like, yeah, and it seems to be way more expressive for capturing the query document in relationship. So before we jump into the next like the V2 of ColBERT, I wanted to ask you to reflect a little bit about what has been the significance, because like you have mentioned ColBERT a lot, and it seems like it has had a pretty big impact in the IR community as becoming kind of like some standard to compare your method to for a couple of years. Yeah. Why do you think that is? Like why did ColBERT become so popular?
Probably a lot of reasons. A less interesting reason is the timing. It was just one of the first models, but it was one of the first models, and it's very effective. So it's effective within the domain. I'm not sure what the current state of the art is. Maybe there are single vector methods that are similar to ColBERT when trained on MS Marco within that domain. I'm not totally sure. But last I looked, this is not possible without a lot of extra engineering tricks going into that single vector method that might also improve ColBERT. I don't know if they would or not, but so it's very effective within the domain, possibly more, but also it transfers well outside the domain. So looking at benchmarks like BEIR, which of course didn't exist at the time of the first paper, it seems to be hard for single vector methods to perform well there. Maybe this is just something we haven't found. Maybe it's just a detail of the training. I don't know. But whatever it is, ColBERT clearly transfers well here to these out-of-domain data sets, where single vector methods really struggle to outperform BM25. We started to look at some a few episodes back, like Spider, where they're barely beating BM25. But ColBERT would be better than this right away.
That's so interesting, because actually, like indeed, when you look at the two papers, ColBERT and ColBERTv2, you definitely see a very stark difference in the sort of the benchmarking culture or something, right? Like ColBERTv2 very much focuses on what you were saying about like kind of domain transfer or kind of this robustness, whereas ColBERT1 only only tests on MS Markov, right? Which is, you would say, is pretty much just in domain.
I would call it in domain
evaluation. And it's kind of interesting because ColBERT is precisely strong, like you were saying, in out of domain, or kind of like this kind of transfer when compared to the dense retrieval.
It's unclear why, but one clear difference is that it has a vector per term. So maybe something about anchoring it to the term level is more robust.
Yeah, I mean, in the last episode, we precisely were talking about how the difference between dense retrieval and cross-encoders, how the performance degrades when you start doing out-of-domain evaluation. And it seemed to be like cross-encoder, these models that took into account all of the terms. So basically modeled all of the query terms and document terms. Cross-encoders suffered less, right, in these out-of-domain, whereas the dense retrieval models seem to suffer way more. Intuitively, maybe because, like these representations, kind of these single embedding representation kind of just are too optimized for the domain they're trained in, or well, I don't know how you would.
I mean, just in terms of bits, it's a lot smaller. I don't know if that's the key point, but I mean, it's one vector versus document length vectors. So it's at least 2 orders of magnitude different as far as capacity. If that's the key difference, I'm not sure, but yeah.
All right. So like we just said, ColBERT become very famous, pretty much a gold standard, like one of the standard models that you should add in your tables when you compare your models. So now fast forward to a few months ago, ColBERT v2, which is pretty much kind of like a next step, building on top of ColBERT, making it more modern with the modern techniques. So what is ColBERT v2?
They improve this in 2 ways, I would say. One is they take dense retrieval state-of-the-art training techniques and apply them to their training paradigm. The second is they have this novel way of storing document embeddings using clustering and centroids that makes things faster. Maybe we start with the training techniques. These are more general. So they basically use hard negatives. They have a mini-LM, I believe, cross-encoder, and they follow Rocket QA's system, where essentially they're using a KL divergence loss to try to train ColBERT to mimic the score distribution from the cross-encoder, I believe. I guess this is a hard negative. This goes back to our earlier discussion. I don't know if my earlier definition applies directly here or not. But they're taking a strong model, a cross-encoder, and trying to mimic its behavior, essentially. So it's...
You could say it's a distillation, right? As well, you can use that term.
It is definitely trying to... it's distillation from the cross-encoder.
Okay.
I believe they train ColBERT once at following V1, and then they distill it from there, rather than distilling from scratch.
Okay.
And then they also use in-batch negatives on top of this, I suppose. So they call this training with hard negatives.
The section we're talking about is 3.2, right?
Yeah. So they have this distillation, and then they additionally use the in-batch negatives.
The in-batch negatives, and then do like standard cross entropy.
So some combination of in-batch negatives and distillation, which they call denoising training with hard negatives.
So these alone already seems to help a lot in performance, right? By the way, all of the rest, when we don't say anything of the rest of the model stays the same, like the maxim operation, like all of these pretty much stays the same.
It is, yes.
But like Andrew said, they do some knowledge distillation that seems to work, has proven to work well for other models like dense retrieval.
This knowledge distillation from a cross-encoder is a pretty common technique now.
How long has it been a standard technique for training dense retrieval? Or
maybe a year, maybe a bit more than a year.
It's not so much.
But I mean, my sense of time, especially coupled with the pandemic. But within the past year or two, I mean,
All right. And is this so we have the distillation, the in-batch negatives that
Yeah, this is the training improvement, and then they also have this. Let's call it an indexing improvement, I guess.
Okay, yeah, like efficiency, yeah.
Yeah. So you could take this with these improved training techniques and just apply it as is, but they do some things to speed up or essentially to lower storage costs. So they cluster. So they process a collection. They have now embeddings for all the documents in the collection, all the terms in all the documents specifically. They cluster this. Now they have a bunch of centroids, right? And so they store each of these term embeddings as basically the ID of their nearest centroid plus a heavily quantized delta vector. So they store centroid ID 1, 2, 3. This gives you a vector corresponding to that centroid.
Yeah.
And then they also store a vector with only 1 or 2 bits per dimension. That's basically the delta between the original embedding and the centroid. So what you do is you take the centroid vector and you add this delta vector to it, and now you have an approximation of the term embedding you started with. And so this has clear storage space improvements because you're storing the centroids once and you're storing the delta vectors, which are only 1 or 2 bits per dimension, so much, much smaller.
So this basically reduces the storage footprint of your index, right? Like how big that is. But in terms of because at inference, when you want to search through the space, basically like do the nearest neighbor search that we talked about before. This does this also improve the latency or like the speed at which nearest neighbors can be retrieved?
Yes. So you can find the top centroids, first of all. I believe they compare against all centroids in this paper. They actually have follow-up work that I think was becoming too much, where they only consider the top centroids in the scoring mechanism.
I see.
I believe here they're including all of them, but later work, PLAID, the paper, suggests.
To give a sense of scale, how many clusters are we talking about? Like, what would be like a typical document collection size that they work with? What would be a number of clusters, right, that they work with?
Yeah.
And then like the size of each cluster.
It's quite a few clusters, but I don't want to say the wrong number. Let me find it again. Maybe I'll get it out of my email. So they say the total number of tokens, so across documents, is something like 600 million. They clustered these into about 262,000 clusters, so 2 to the 18th. And then they say that typically a token appears in a few number of clusters. So I don't know, if you have Amsterdam, it's not that it can appear in every single cluster. There's some subset of, 5, 10 clusters that Amsterdam is normally associated with. But maybe different census correspond to different clusters, or maybe different contexts, different topics, something like this.
Yeah. So you would associate kind of clusters to more or less map to different different kind of flavors of or meanings of tokens, right?
Yeah, so they have like, if they look at photos, then they map photo to clusters and they look at what else is in the clusters. So there's one cluster with like photos plural, pictures. There's another that's like photo, image, picture, photograph. Another like picture, image, artist. So all about photos, but one is like photograph, one is about artist, one seems to just be about synonyms of photos, something like that. So there's some combination of term sense and topic.
Makes sense. Okay. No, sounds...
Yeah, so it's something like learning the right version of a term and then having a small delta to tweak that a little bit.
Yeah.
So this is like photo that goes with artist, and then we use that delta vector to slightly tweak it, which I guess can only make each dimension a bit bigger or smaller. It can't change anything too much because you're saving 1 or 2 bits.
Yeah.
So I think of this as scaling up or down the magnitude of each dimension, and maybe.
Yeah, it makes sense. Yeah. All right. Yeah. Sounds reasonable. So, and to get a sense of how much this hurts performance, they have a couple of numbers also in Appendix B, right? Where basically we're talking about just a few decimals of percentage in MRR, for instance, performance drop, right?
Yeah. Very, very little drop from this technique. It's basically just a free space savings with no real downside, it seems.
I'm guessing, would you expect to have a pretty big implementation kind of like complexity.
Well, that's true. Yeah. So this is yet another dimension. Like, I mean, obviously, it's much harder to implement, I suppose. Before, I think you could have just thrown it all in FICE. Now, I don't think they do. I haven't gone through their code extremely closely, but I think they're implementing all of this, like the centroids and so on. I mean, using FICE to help, perhaps, but I don't think it's something where you easily can just outsource it to another library. The centroid plus delta is a bit custom.
I mean, if it's a very effective form of compression, it will probably be implemented in some of these libraries off the shelf and become pretty easy, right?
Yeah, I mean, maybe this will be, but as far as I'm aware, it's not standard. Yeah.
All right, I think that covers the main points of the method. Can we jump into the results? So what first, like what data sets or benchmarks are they benchmarking these on, and what are the baselines that they're comparing it against?
So they have 3 data sets. I think we'll focus on the first 2. So MS Marco, we've talked about a lot. BEIR, we've also talked about. This is just testing generalization. So you just test on these data sets, you don't train on them. And then they created this new LADA data set. They derived it, I guess, from some of these question answering websites. It's top answers across different domains. But I think the others are easier to focus on because we have comparison points in other papers and so on.
So would it be fair to say that MS Marco results sort of test in-domain performance and BEIR tests more the generalization aspect or out-of-domain performance?
Yeah, exactly. So if we look at MS Marco, ColBERT is better than the baselines they consider. The strongest baseline they consider is RocketQA-v2, which is one of these dense retrieval methods with advanced training techniques, essentially. They use some of these, I believe this was what they followed for their training, so like the scale divergence distillation approach, for example. But so let's see, if we look at MRR, this RocketQA is 38.8, ColBERT is 39.7. So an improvement, not a huge improvement, but it is better. It's at the top of this table.
And do you know how this compares to other state-of-the-art cross-encoders, like the actual top of the leaderboard on MS Marco?
I don't know what the top of the leaderboard today is, but I know, for example, if you take a cross-encoder and train it well, doing nothing else, just like an electric cross-encoder with a loss considering many negatives, you get around 0.404, I believe. At least 4.0. So it's slightly better, but it's not a huge improvement. The top of the leaderboard is above that, maybe around 4.1 now. I'm not sure exactly, but
so
not a huge improvement, but above it. And then if you compare to the original ColBERT, it's a pretty good improvement. So 36 to 39.7. And really, I think this is coming from the improved training. The centroid technique should improve speed or storage requirements, which improve speed, but I don't think it's doing anything to improve effectiveness.
No, that makes a lot of sense, and that gives you again like bit of perspective of how much the performance of these models are due to the optimization tricks and techniques, right? That keep just getting better. I would say the distillation is the main driver of this improvement. Would you say that's
No, this distillation from a cross-encoder seems to be very effective. Sometimes people do this and then use it to create hard negatives. I don't know if this counts as hard negatives anymore, going back to our earlier discussion, but this is a really common approach too. Like there's these standard, like essentially labels that are from cross-encoder scoring methods, and people use these.
The labels which can be like even better than MS Marco labels, right?
You're like trying to mimic a cross-encoder's confidence, for example, right? Rather than just using the...
No, but I meant to reference actually it was like the first paper actually we talked about that in some, depending on how you define it, these cross-encoders might get you better labels than the actual annotations.
That's true. Yeah, they were often better than the ground truth.
Exactly. Anyway, let's talk about the BEIR results, which are also interesting in the more generalization aspect of things.
So I guess we see a similar trend here with ColBERT outperforming the others. The baselines are slightly different here. If we look at RocketQA2, so this is a shared baseline, there's a pretty big improvement for many of the tasks. There's no average on the data set for good reason, so it's hard to say. But for example, the DBpedia is 35 versus 44. I don't know, Trek COVID is 67 versus 73. Hotpot QA is 53 versus 66. So Rocket QA is a much bigger hit in performance going out of domain, it looks like.
Right. Yeah. Right. And none of the methods here as baseline are cross-encoders, are they?
I believe not. But so most of them are dense retrieval. There's also PLAID-v2, which is the second best method after ColBERT-v2 here. This is also term-based, but it's learned sparse retrieval. So it's using an inverted index with these learned term weights. And this one is better for a couple data sets, but generally not. But it's much more competitive with ColBERT, which again is interesting because you see that these methods with the term-based weights are the competitive ones here.
I guess an interesting thing to point out, though, is that PLAID-v2 does seem to be outperform a little bit ColBERT-v2 in the semantic relatedness tasks.
So they split here, BEIR here, which I like, into search and then relatedness.
Okay. Can you actually describe what these two categories of benchmark are?
So as far as I'm aware, that's not an official split, but what they mean is that relatedness, if you look at the some of the corpuses in here, like argue-ana, there are things like find the counter argument for this or find an argument for this position. So it's some task that's more specific or different than standard ad hoc search. There's some extra interpretation of the query, I guess. So for these, PLAID does seem to be a bit better on some of them, most of them. And then for the search tasks, ColBERT is a bit better for most of them. But yeah, I'm not sure why that split is there. It's interesting.
All right. So, what would you share? Like, what would you take from these results? I mean, is there any kind of takeaway?
Yeah, I guess a few things. So one is that the story hasn't really changed from ColBERT v1. I guess the paper didn't make the case for out of domain, but I think people started to pick up on this was working out of domain after the paper was released. And the story hasn't changed as far as that, right? In domain, it's pretty competitive with other methods. Out of domain, it seems to be better than single vector dense retrieval. Another point is that these training improvements that work for the single vector dense retrieval seem to work just as well here. So things like that distillation, where it was tried before with these single vector methods, seem to work with these per term vector method, ColBERT, just as well. That's interesting. And then also this observation I made a few times that the generalization seems to be tied to the fact that they're using term level representations, either with PLAID where you get one score per term or ColBERT where you get one vector per term. These are the methods that work well in the generalization. Again, I don't know exactly what's causing that, but it seems like something that's coming up a lot in results.
So would you expect this, if you look at the crystal ball of the future, would you expect these to be a pretty fundamental limitation that kind of dense retrieval models never sort of overcome, and then like this just becomes kind of the standard technique for?
I would be hesitant to make that prediction. It's very strong, but I'm not sure. I think that if you just increase the size of a dense vector, it's not going to work because this will be hard to train, right? If you were to increase the representation capacity to match what these term-based methods have, which would be inefficient, you wouldn't want to do that, but just as a test to try and understand what's going on, I think the test would fail because it would just be hard to learn, a vector with 100,000 dimensions to represent the document. So I'm curious about what will happen here, but I don't know. I think one angle is to think about why this works better and try to change single vector representations in some way. I don't know exactly how, but maybe reconstructing the important terms that went into the representation, or I don't know. I mean, there's room to play here, but it's unclear exactly what should change to improve this property.
Yeah. I guess another interesting thing that they don't do here is basically, as far as I understand, there's no pre-processing applied to the the terms that are like that you search through the terms. Part of these max similarity scores are computed across things like stopwords and all of these, right? This is not the thing that is kind of explicitly modeled. You just kind of expect the model to learn that, like to kind of filter that out, or like, do you have any, I don't know, like I don't think they introduce, so they show any result or experiments on this, but do you have any sort of intuition on the qualitative behavior of what the scores of ColBERT actually are doing? You know, if you look at these query terms, like you have a query, right? Like how the...
Yeah, I mean, I think it's a very good question. So as far as needing IDF, I know other models like PLAID seem to learn some idea of term importance, and then this seems to remove the need for IDF. Also with word pieces, I'm not sure what IDF really does here. Basically, you have a cutoff, or something like a cutoff, where you never have an extremely rare word because you would have just never generated the word piece for it.
Yeah.
This would be tokenized as several more common word pieces.
Yeah.
So there's like a ceiling on the IDF. You can't have something really uncommon.
Yeah.
I don't know how this interacts with things either.
That's such an interesting point. It might be that that this model is very sensitive to the vocabulary size, right?
Maybe.
That it might become much better or much worse if you, instead of like 30,000 words, you take like 10,000 or 60, 100,000 or...
It's possible, yeah. I think there's been very limited experimentation of changing the vocabulary just because it's really painful to do. You have to go all the way back to the beginning.
You would have to train BERT
Yeah.
from scratch, which is, pretty painful.
I think it's very interesting to explore, but it's not an easy direction to explore. Yeah.
No, absolutely. There's a lot of kind of interesting ramifications, but... Anyway, so I guess we're just approaching the end of the episode here. If we kind of do a bit of a recap on the existing neural information retrieval methods, right? You would say we have, like we said at the beginning, like the 2-tower biencoders, something that calculates a representation for the query for the document, right? And then like it's a 1-to-1 similarity score that you do on an index. Then you have like a full cross-encoding, which is something like the rerankers do, like just have a transformer, you feed the whole query, whole document, and calculate the score, which does very well, but it's super expensive computationally. Then we have ColBERT, which is a sort of late interaction method, right? Which is you can calculate offline representation for documents, but then you do a bit of a more complex distance calculation between all the terms in the query and all the terms in the document. That seems to work very well, and it's a very good trade-off between efficiency and performance. And then we have talked a couple of times about more like a paradigm changing kind of approaches like autoregressive search, in which some kind of model kind of just generates IDs of retrieved documents. So what do you make out of all of this space, and like where are you more more personally interested in kind of like looking into, like in your own interest, like where do you think the kind of the most of the low-hanging fruit is going to come from in the next year or two?
Yeah, I mean, I think they're all interesting. I think that because cross-encoders were around first, there's probably much less low-hanging fruit there, which doesn't mean there's not harder to find fruit that's very impactful, right? But I mean, this is clearly the most well-studied. I think the least studied is like the learn sparse retrieval, like this PLAID, learn something to put an inverted index.
Okay.
ColBERT is somewhere in between, I guess. There's a lot of work on dense retrieval, but less on ColBERT's approach specifically, I suppose, of this, one vector per term. So I think taking this further in terms of efficiency is interesting, but I think that with this V2 and then a recent work like PLAID, for example, is a paper on arXiv by these same authors where they speed it up a bit more, basically just improving the implementation. ColBERT is already quite efficient. So to me, this question of why ColBERT behaves differently than single vectors is one of the most interesting.
Okay.
Like, what can we do to make a single vector method more robust? Is one way to come at it, and I guess the other way to come at it is to try to make ColBERT nearly as efficient as a single vector method. Which is happening primarily, I think, with these implementation improvements, like the clustering, these delta vectors. All of it's improving the speed a lot, specifically storage space, which was where they had trouble.
I guess one other interesting thing to reflect on is it seems like since 2020, like since more than 2 years ago or something, there's kind of like recurring evidence that, for instance, this type of method that takes into account all of terms or cross-encoders work much better than the dense retrieval single vector models. At the same time, there's still so much research and so many people who are focusing on that mode of dense retrieval, of like single vector to single vector. What do you think that is, that it's still such a popular thing to try to improve, while it seems to still be kind of weaker in terms of performance than other methods?
Yeah, I think it has a few attractive properties. One is that you can just use an approximate nearest neighbor index with it directly. You don't have to do this ColBERT, like re-ranking with centroid, whatever, this stuff. You just throw it into an ANN, so that's kind of nice. I suspect also people like the simplicity, or what they feel is the simplicity of just having one vector for the document.
Yeah.
To me, I don't know if that's actually simpler than some of these, but from like a deep learning API perspective, just having a vector is somehow more in the spirit of how people want to do things, I suppose. That's probably a large part of it.
Okay. No, I mean, that makes a lot of sense in terms of like this kind of like more abstraction beauty. It's kind of like in terms of like it has some kind of appealing properties. Do you know of any work that does these sort of many-to-many distance calculation in a bit in the same spirit as ColBERT does, but at a different sort of granularity that is neither document, neither terms, but it's more like every, I don't know, at the sentence level or at the paragraph level?
No, I don't think I know of anything like that, at least at the transformer level. Actually, pre-BERT, there was a model called deep tile bars by Grace Hui Yang from Georgetown and some others. And what this did is it basically built a similarity matrix, like we've talked about, and then you can do something like maxim on the similarity matrix to score. But the similarity matrix was, if I remember correctly, between document passages and query terms rather than individual document terms. So they kind of rolled up the passage to a representation and then use that representation to get similarity with query terms, and then built the similarity matrix off of that. So something like that could be applied to ColBERT, right? You just need some aggregation step in between to take the term embeddings and turn them into, I don't know, a sentence embedding or a 5-gram embedding, or whatever it is. I guess this would have storage. It's more storage efficient as well, right? If you just divide by some constant factor. But it's interesting they don't try this way. I'm not sure why or why not. I mean, maybe it's easier just to reduce the dimension size of individual terms, which is what they do, right? So they go from 768 to like 128 or even 24 dimensions for a term embedding. Yeah,
exactly. I mean, if you think about it, it shouldn't be that, like for instance, if you only say train this, did like ColBERT and only use the CLS token or like the special token that they use, this would in a way be already this kind of like, you could calculate some, do this maxim operation, but on class always on CLS tokens and each query term or something like that. And that would be kind of some kind of different granularity.
I think this even goes back to your question about why people prefer single vector. It's like from a deep learning perspective, this is a lot of messing with the architecture that I think people don't want to do right now. Right. So we're talking about adding something like a CNN or a transformer with attention only over a certain window, whatever. I think people don't want to handcraft that part of the architecture. But I think it would be interesting to see what happens though.
No, I totally agree with that. So do you think that there will be another version of ColBERT, or if you were to do a ColBERTv2, what would you expect the kind of newer stuff you would include in this?
I mean, that's a really good question. I mean, maybe they find a way to improve the centroid approach more, maybe fewer centroids, I don't know, some other optimization in there. Like I hinted at, they have a paper on arXiv where they do pruning. So they don't compare against terms from every centroids. They figure out which centroids are the ones that are close to query terms and then ignore the terms that aren't from those, which saves you a lot of these term reconstructions with centroid plus delta vector. So maybe, improvements along these lines. Beyond that, it's very hard to say. So if there were new, dense retrieval techniques that could be applied, I'm sure they would be. I think right now they're at the state of the art as far as what to apply. At least I'm not aware of something clearly better that should be applied. But I think just the key point of improving storage efficiency is really, what will change here, because they're already there in terms of robustness and effectiveness.
Yeah. Although I have to say that I'm kind of surprised that that's such a focus of this paper, right? This aspect of storage efficiency, because I normally associate academic research with not being very concerned about that, as in like it doesn't affect the benchmark scores and why do people or does the community, do you get a sense that the community really cares about this sort of efficiency trait or
for storage efficiency, not generally. I mean, storage is cheap, right? But the thing is, it started so painful that it would have been really hard to experiment. So in the ColBERTv1, they're still down projecting their vectors to a lower dimension, like 128 or 24. But if you were to save the 768 dimensional vectors from ColBERTv1, I believe I calculated a few terabytes of disk space just to save that collection. If you're doing a hyperparameter search, this is a few terabytes per hyperparameter. It's not that the community cares a lot about storage necessarily, but it's starting to make experimentation just really painful if you don't do anything to optimize it. They're already better than that, right? So for ColBERTv1, it's something like 200 gigabytes for MS Marco. But this is going to add up. Disk I/O takes time, right? Maybe in academia you're not using SSD for this. It will be painful for you, I think, if it's not a huge concern of the community.
Okay, no, that's very interesting. All right, do you have any other thing you'd like to highlight from this work we haven't touched on?
I don't think so. Maybe just a quick pointer towards that other archive paper, PLAID, PLAID, by the same authors, where essentially they do centroid pruning and then they don't use these delta vectors in the first retrieval step, which is cheaper because they just compare against centroids rather than comparing against many more terms. And then they re-rank that with the vectors. So they get the benefit of them, but basically they're not needed for recall. So they get additional big improvements.
All right, so I will have a superimposition of the... all right, so thank you very much for joining us, and I'll see you in the next episode.